Hello, good morning all of you. Welcome back to the open channel flow. We have been discussing for the past few classes about the fundamentals of the open channel flows, the types of open channels, and the classification of flows in open channels. Then the velocity distribution in the last class we discussed. So in the velocity distribution, we have seen just like a pipe flow, in open channel flow also, there would be a different velocity distribution in view of the resistance being offered for the flow, not only from the boundaries and bed of the channel, but also from the overlying atmosphere. So this results in a non-uniform velocity distribution at a given section in an open channel. And this velocity distribution more or less is similar, but it is not the same as compared to the different shaped open channel sections, like rectangular section, rectangular channel section, trapezoidal channel section, circular channel section, triangular channel section. We have seen the velocity distribution is different. But it is not same, but it shows a similar pattern, which indicates that the maximum velocity will not occur at the free surface. However, it would be slightly below the free surface. Further, for all the calculations of energy and momentum or for various applications, we go by the concept of average velocity or mean velocity, as a result of which there would be a difference in the total kinetic energy calculated based on the actual velocity distribution to the mean velocity calculations. So to account for this, a factor known as kinetic energy correction factor alpha. Similarly, the momentum correction factor beta are introduced. In the previous classes, we deduces the expressions for the kinetic energy correction factor alpha and the momentum correction factor beta, followed by working of the calculations for alpha and beta in some of the shaped channel sections. Today, we are going to discuss about the uniform flow in the open channel and what are the governing formulae for the uniform flow in the open channel, like Chase's formula, Manning's formula, Bayes' formula, and so on. By definition, already we classified the flows. By definition, what is uniform flow we know, what is non-uniform flow we know. So by definition, uniform flow is the one in which the flow characteristics like the depth of flow, velocity, etc. do not change with respect to space, with respect to section. So with respect to the position, from one section to the other section along the length of the channel, if the depth of flow is constant, we say the flow is uniform. Just look at this figure. This is the channel bottom, and you have the uniform flow here, where at different points or at different sections along the length of this uniform flow portion, the depth of flow is constant. The depth of flow is constant. Followed by, there is a steep slope in the longitudinal slope of the channel, which may be resulting in a non-uniform flow. Then once again, uniform flow. So this can be depicted through this figure where the depth of flow is varying from one point to the other point along the length of the channel. Along the length of the channel. So uniform flow by definition is the one in which the depth of flow, velocity, etc. become constant. Okay, so this is about the uniform flow. What are the main features of this uniform flow we are going to discuss, and what are the formula for analyzing this uniform flow, like Chase's formula, Manning's formula, Darcy-Weisbach equation, friction factor as applicable to the open channel flows, and what are the various factors that would affect the Manning's roughness coefficient, which may be a part of this Manning's formula. So a flow is said to be uniform if its properties remain constant with respect to distance. So with respect to the space, with respect to the section, if the depth of flow is becoming constant, then we say that the flow is uniform. So a flow is said to be uniform if its properties remain constant with respect to the distance. In the figure, you may observe that there are two sections, say section 1, where the depth of flow is y1, section 2 on the downstream side, where the depth of flow is y2, and if y1 is equal to y2, which means that the flow becomes uniform. Which means that the flow is becoming uniform. So the properties remain constant with respect to the distance. So there is a distance L apart, maybe for the section 1 to section 2 in the uniform flow, which is shown in the figure. So if the depth of flow at section 1, y1 is equal to the depth of flow at section 2, y2, then the flow becomes uniform. So the depth of flow is constant at all sections in a uniform flow. So this is one of the prime most important feature of the uniform flow. The depth of flow remain constant. If you consider two sections, say section 1, section 2, then the depth of flow at section 1 is y1, the depth of flow at section 2 is y2. If y1 is equal to y2, which is equal to y, then the flow is uniform. For a prismatic channel, say for a rectangular channel, if you take, what would be the wetted area or the cross-sectional area at section 1? It is the bed width multiplied by the depth of flow. Bed width multiplied by the depth of flow, B into y1. Similarly, here also it becomes B into y2. So the wetted area at section 1 would be equal to the wetted area at section 2, A2. A1 is equal to A2 because you are taking the bed width B also is constant because you are taking a prismatic channel. So if a rectangular channel is considered, B into y1, the wetted area at section 1 is equal to B into y2, the wetted area at section 2, since y1 is equal to y2. Since y1 is equal to y2, a1 also would be equal to a2. That means wetted area at section 1 is equal to the wetted area at section 2. So if you take the continuity equation, the discharge Q is equal to area into velocity is constant. We know that there are three basic equations which would be governing the entire fluid mechanics principles, like the continuity equation, the Bernoulli's equation, the momentum equation. Continuity equation derived based on the law of conservation of mass. So which gives that the total, the value of A1 V1 in a simple one-dimensional flow analysis, the volume rate of flow along the length of the channel at different sections would be constant. In other words, to say, it would be Q is equal to area into velocity, A into V is equal to constant. A, in our case, is the wetted area. V is the mean velocity at a given section. Mean velocity at a given section. So Q is equal to A into V is constant, which means that A1 V1 must be equal to A to V2. If you take two sections, A1 V1 must be equal to A to V2. Since A1 is already equal to A to here, A1 is equal to A to here, V1 also will become equal to V2, which is equal to the mean velocity V. So another important feature of the open channel flow that we have arrived in the case of a uniform flow is not only that the depth of flow y1 is equal to y2, but also the mean velocity at section 1 v1 is equal to the mean velocity at section 2 v2. This is the second feature of the uniform flow in a open channel. Y1 is equal to y2, the depth of flow is constant. Then the velocity v1 is also equal to v2. The velocity v1 also is equal to v2. So if v1 is equal to v2, what will happen? At section 1, v1 square by 2g, the velocity head. The velocity head, v1 square by 2g. At section 2, the velocity head is v2 square by 2g. Since v1 is equal to v2, at both these places, v1 square, v square by 2g, here also v square by 2g. Same intercept will be there. Same vertical intercept will be there at section 1 as well as at section 2. Which indicates that in the case of a uniform flow, the top water surface, which is known as the free surface, and the total energy line or the energy gradient line are parallel to each other. Why it is happening? I repeat once again. We are considering the uniform flow. By definition, uniform flow is one, the depth of flow is constant. Y1 is equal to Y2. If you apply the continuity equation, A1 V1 is equal to A2 V2. Since A1 is equal to A2, for a prismatic channel in uniform flows, then what will happen? V1 also will be equal to V2. Since V1 is becoming equal to V2, V1 square by 2G, the vertical intercept at section 1, and V2 square by 2G at the vertical intercept at section 2 are equal. As a result, the water surface and the total energy line are parallel to each other. Further, since you are having a prismatic channel here, with respect to the datum, the longitudinal slope of the channel also is constant. So, in a uniform flow, in open channels, the channel bed, the water surface, and the total energy line are all parallel to each other. They are all parallel. In other words, the slope of the channel bed is equal to the slope of the water surface is equal to the slope of the total energy line. This is the third important feature of the uniform flow. Three features that we have identified. Number one, for a uniform flow, the depth of flow remains constant. Y1 is equal to Y2. Number two, on application of the continuity equation Q is equal to A1 V1 is equal to A2 V2, the velocity remain constant. V1 is equal to V2 for a prismatic channel. Number three, the slopes of the channel bed, water surface, and the total energy line are all equal. So these are the three important features of the uniform flow. So it follows that in the uniform flow, and thus in a uniform flow, the depth of flow, the area of cross section, also we call wetted area, and the velocity of flow remain constant along the channel. And uniform flow is possible only in the prismatic channel, because we made an assumption that for a prismatic channel, A1 is equal to A2, because the bedwidth is not changing there. Say for a rectangular channel, if it takes so, if the channel is prismatic, then only uniform flow is possible. Since V is constant, V square by 2G also becomes constant, which is the elevation above the water surface. So the slope of the total energy line, the slope of the water surface, and the slope of the channel bed are all equal. Slope of total energy line, slope of water surface, and slope of the channel bed. All the three are equal. What are the various formulae that are available for analyzing this uniform flow in open channels? Say, let us take up one by one. Say, Chezy's formula. Chezy's formula is one very powerful semi-empirical formula which may be used for analyzing the uniform flow in the open channels. You are considering a control volume approach. This also you have studied in fluid mechanics. What is a control volume? It is a volume formed between any two sections of the flow. So this is section 1, this is section 2. In between the two sections, the volume formed is the control volume. The channel bed is there, and you are considering the longitudinal section of a channel section, and two sections 1 and 2, and the volume formed in between these two sections is the control volume. And in the case of a uniform flow, since the velocity is constant, the velocity at section V1 is equal to the velocity at section V2. Since there is no change in velocity, acceleration becomes 0. This is another point. The acceleration becomes 0. There is no there is no acceleration in the uniform flow. So in a control volume approach, if you observe closely this figure, you may identify with respect to the horizontal datum, we have considered a longitudinal section of a uniform flow. With respect to the horizontal datum, the longitudinal section is having certain slope. Have you noticed? The longitudinal section of the channel bed is having certain slope. Why the slope is available? Unless the slope is there, flow is not possible. So to have the motion of water in the canal or the channel by the action of gravity, a flow is provided. So the slope is provided. So this longitudinal slope is provided for the channel with respect to section 1 to the section 2. So the volume which is formed in between these two sections along the flow is called the control volume. So what are the various forces that may be acting on this control volume can be analyzed easily, so that you will be able to arrive at the Chezy's formula. Let us look at section 1, the depth of flow is Y1. The depth of flow is Y1. Similarly, at section 2, the depth of flow is Y2. Then V1, let V1 be the velocity at section 1, let V2 be the velocity at section 2. So because we are taking a control volume between the sections 1 and 2, what are the various forces that may be acting on this control volume? What are the various forces that may be acting on the control volume? You may notice here that there will be a hydrostatic pressure force which may be acting at section 1 along the flow direction, P1. Similarly, there may be hydrostatic pressure force which may be acting in the opposite direction, having a value of P2. So P1, P2, hydrostatic pressure force is acting at section 1 and at section 2. Apart from that, since the flow is taking place along the length of the channel, there will be resistance to the motion. So F, the force due to friction, which may be opposing the motion, may be there acting in the opposite direction. So you have hydrostatic pressure force P1 at section 1, hydrostatic pressure force P2 at section 2, and the frictional resistance which is opposing the motion FF, which is opposing the motion. Apart from these three forces, since you are considering a control volume, the self-weight of water also you need to take. So this self-weight of water will act through its CG vertically downwards. So its component, of course, if you have the inclination with respect to the horizontal for this channel bed is theta, correspondingly W sin theta will be the component of the self-weight of water acting along the flow direction. So as we have noticed, there are four forces which are acting on this control volume. Hydrostatic pressure force P1 acting at section 1 along the flow direction, hydrostatic pressure force P2 acting at section 2 opposing the flow direction, then frictional resistance FF opposing the flow direction, and lastly the component of the self-weight of water W sin theta acting downwards, normal to the flow direction. So considering a uniform flow of water in a channel, as the flow is uniform, the velocity, the depth of flow, the area of flow will become constant for a given length of the channel. But for arbitrarily, we have taken V1, V2, Y1, Y2, etc. Later they become equal, right? A is the wetted area. Theta is the inclination of the channel bed with respect to the datum. And S is the longitudinal slope of the channel. The longitudinal slope of the channel is S. V is the mean velocity of flow of water. P is the vectored perimeter. By definition, we know that it is the length of the channel boundary which is in contact with the flow. It is a vectored perimeter. F is the frictional resistance per unit weight of water, per unit area and per unit velocity. And W, the weight of water between the sections 1 and 2. And to get this weight of water, W in between the sections 1 and 2, you may observe here that this is all the volume of water. So the volume of water multiplied by the specific weight of water gives you the self weight of water in the control volume. Self weight of water in the control volume. So if A is the vectored area and L is the length between the sections 1 and 2, then A into L, area multiplied by the length, gives you the volume. Area multiplied by the length gives you the volume. And if this volume is multiplied with a specific weight or unit weight of water, you will get the self weight of water gamma AL. But this acts vertically downwards. So its component, of course, would be W sin theta. So gamma AL sin theta is the component of the self weight of water along the flow direction. Similarly, the frictional resistance against the motion of water would be, if F is the frictional resistance per unit area per unit velocity, the total frictional resistance will become F into surface area multiplied by the velocity to the power N, where N is an index which is considered to be equal to 2 for this case, and hence the surface area would be actual area which is in contact with the flow through this control volume from section 1 to section 2. If P is the vectored perimeter and L is the length, the total surface area will become P into L, and hence the frictional resistance will be F into P into L into V square. So we have now identified and quantified two major forces acting on the control volume. One major force is component of the self weight of water along the direction of flow, and the second is the frictional resistance which is opposing the motion. I would like to just explain once again how do you get this frictional resistance against motion of water. I'll just go back to the previous slide I'll just go back to the previous slide. FF is the frictional resistance which is opposing the motion. So this resistance will be offered by the flowing fluid not only from the channel bed but also from the sides of the channel. So if P is a wetted area, then the frictional resistance per unit weight of water, per unit area and unit velocity gives you the total frictional resistance. So to get this total frictional resistance, the F, the frictional resistance per unit area per unit velocity multiplied by area multiplied by velocity to the power n. N is index considered to be equal to 2, and the surface area would be the total area which is directly in contact, that means wetted perimeter multiplied by the total length, multiplied by the total length of the channel which is considered between the two sections 1 and 2. So the surface area will become P into L, and the frictional resistance against motion would be equal to the F multiplied by the surface area P into L multiplied by V to the power n becomes V square here. So F into P into L into V square is the frictional resistance which is opposing motion, and component of sulfate of water gamma A sin theta which is along the direction of motion. In fact, both are in two mutually opposite directions. That's component of sulfate of water along the direction, frictional resistance opposing the motion. There are two more forces actually. What are those two more forces? The pressure force acting at section 1, hydrostatic pressure force. And similarly, hydrostatic pressure force acting at section 2. The depth of flow of water at section 1 and at section 2 are same. Hence, the pressure forces acting on these two sections also are equal, but they are acting in the opposite two directions, and hence they may be cancelled. This is how P1 and P2 have not been quantified. Hydrostatic pressure force at section 1, hydrostatic pressure force at section 2 in the control volume approach, they act in the mutually opposite directions. Since you are considering the uniform flow, Y1 is equal to Y2 and V1 is equal to V2, because the cross section or the wetted area at section 1 is equal to the wetted area at section 2, so P1 will become equal to P2. Since P1 and P2 are acting in the mutually opposite directions, they get cancelled. So you are left with only two forces. One is the component of the sulfate of water along the direction of flow. Number 2, the frictional resistance acting against the motion of water. There are two forces. Now applying the Bernoulli's, the Newton's second law of motion. In the case of uniform flow, the velocity is constant for the given length of the channel. Hence, there is no acceleration. Because the velocity is constant, the acceleration becomes rate of change of velocity 0. Apply the Newton's second law of motion and resolve the forces acting along the direction of flow. So as per the Newton's second law of motion, the net or resultant force acting in any direction would be equal to mass times acceleration. The net or resultant force acting in any direction must be equal to mass times acceleration. We know the acceleration is 0 because the velocity is constant. Since the flow is uniform, velocity is constant, acceleration is 0. So mass into acceleration or mass into 0 becomes 0. In other words, the net or resultant force acting on the control volume must be equal to 0. How do you get this resultant force? It is the resultant or the algebraic sum of the two forces acting on the control volume. One force along the direction of flow of water and the other opposing the direction of flow of water. One is the component of the sulfate and other is the frictional resistance. So the net or the resultant force would be component of weight of water minus the frictional resistance, which must be equal to 0. Component of weight of water, we have already identified it as, quantified it as gamma AL sin theta, gamma unit weight of water or specific weight of water. A is the vector area, L is the length. A into L gives you the volume of water within the control volume multiplied by unit weight gamma gives you the sulfate of water acting vertically downwards multiplied with the sin theta, component of that sulfate acting along the flow direction. Similarly, F is the frictional resistance per unit area per unit velocity. F into PL into V square gives you the total frictional resistance opposing the motion. So gamma AL sin theta minus F PL V square must be equal to 0. On the right hand side, it is equal to 0. The reason for this is you are considering a uniform flow. The total velocity is constant and hence the acceleration is rate of change of velocity 0. So gamma L sin theta must be equal to FPL into V square, or V square must be equal to V square must be equal to gamma AL sine theta divided by FPL. Can you cancel any of the terms here? Let us see. Gamma AL sine theta by FPL. Gamma by F. Take as one part. Then A by P. We know A is the wetted area, P is the wetted perimeter. A by P is the hydraulic radius. Hydraulic radius. So gamma by F, A by P, L gets cancelled both in numerator and denominator, sine theta. Okay, so the V square, the mean velocity square here. Mean velocity is V square is equal to gamma by F into A by P into sine theta. Or V is equal to square root of gamma by F into square root of A by P into sine theta. A by P, hydraulic radius R, and square root of gamma by F. What is gamma? Unit weight of water. F is the frictional resistance per unit velocity per unit area. Square root of gamma by F, let it be equal to C, a coefficient known as the Chegys coefficient. Chegys coefficient. Then V will be equal to, substituting these values, V will be equal to C into square root of A by P sine theta or R sine theta. For small values of theta, sine theta may be approximated to be equal to tan theta, which is equal to the slope of the channel. Yes. Longitudinal slope of the channel. Yes. So tan theta or sine theta may be approximated to be equal to, yes, the longitudinal slope or gradient of the channel. So the velocity V would be equal to C into square root of R into S. This is known as the famous Chegys formula, which is used for effectively analyzing the uniform flows in open channels. For effectively analyzing the uniform flows in open channels, V is equal to C into square root of RS. C into square root of RS. V is the mean velocity of flow in the open channel. C is the Chegys coefficient. And R is the hydraulic radius, S is the longitudinal slope. Once you get the value of the velocity V, you can automatically calculate the discharge. The discharge Q is equal to area into velocity. As we know, the discharge equation Q is equal to A into V. Q is equal to A into V. So A into C into square root of RS. Or the discharge Q will be equal to CA square root of RS. But this is only the Chegys formula. This is not the Chegys formula. This is using Chegys formula, this is the discharge equation. But the actual Chegys formula is for velocity. V is equal to C into square root of R into S. What is the dimensional formula of this Chegys coefficient C? The dimensional formula of this Chegys coefficient C. C is equal to V by square root of RS. V by square root of RS. And if you substitute the dimensions for it in a melting system, you'll be getting L to the power half T to the power minus 1, which indicates that the Chegys coefficient C is a dimensional parameter. That means it will have certain units for it. So what is the problem? If you have any units for any of the coefficient, what is the difficulty? If you take, for example, the discharge Q is equal to CD into A into root 2GH. Say the discharge equation for an orifice. Have you studied orifice in earlier courses? Orifice, a small opening provided by the side or at the bottom of a tank to discharge water freely into atmosphere. So to get the discharge equation Q is from the fundamentals you must have obtained, like CD into A into root 2GH. A is the cross-sectional area of the orifice opening, G is the acceleration due to gravity, and H is the constant head, of course, maintained with respect to the central line of the orifice opening. Then what is CD there? CD is the coefficient of discharge. If you try to find the dimensional formula for the coefficient of discharge CD there, you will obtain CD is equal to Q by A root 2GH. Q is the discharge. Q is the discharge. That means volume per unit time, L cube T to the power minus 1 divided by A pi by 4 D square L square. Dimension formula is L square, and A root 2GH, 2, of course, no dimensions, G acceleration LT to the power minus 2, and H is L. The dimension formula is L. If you substitute all that, you will be getting M to the power 0, L to the power 0, T to the power 0 as the dimensional formula for the coefficient of discharge CD in orifice. Similarly, for orifice meter, maybe for venturi meter, For all those equations, you would be getting the dimension formula as m to the power 0, l to the power 0, t to the power 0. That means there are no dimensions for it. It is dimensionless parameter. We call it as dimensionless parameter. Whereas in Cheggy's formula, you have a dimensional formula which is not equal to m power 0, l to the power 0, t to the power 0, which indicates that based on the units that you are providing, the value of Cheggy's coefficient changes. The value of Cheggy's coefficient changes. If you are applying this Cheggy's equation in FPS system of units, you will get some value of C. If you are applying the Cheggy's formula in MK system of units, you will get some other value of C. So that is the problem and the difference for a dimensionally homogeneous and a non-homogeneous equations, or a dimensional parameter or a dimensionless parameter. So in the previous case, what we have seen, the Cheggy's coefficient is having a dimensional formula. It is having a dimension and it is not a dimensionless parameter. L to the power half, t to the power minus 1. So you need to be a little careful while making use of these coefficient numerical values based on the system of units that you are adopting in the problem. If you are adopting MK system, if you are adopting CJ system, SA system, MPA system, you need to be careful about the value of C, which is not constant. It varies from one system of units to the other system of units. The second equation that we usually use here in open channel flows is Darcy-Weisbach friction factor. For the purpose of flow resistance, which essentially takes place in a thin layer adjacent to the wall, an open channel can be considered to be a conduit cut into two halves. It is cut into two half portions, and to analyze for this Darcy-Weisbach equation, hydraulic radius R would be considered. Hydraulic radius, as we know by definition, A by P, wetted area by wetted perimeter. A by P, pi by 4d square divided by pi d. Or it becomes D by 4, or D will be equal to 4 into R. D, the diameter of the pipe, would be equal to 4 into R. Take the Reynolds number, it will be Vd by nu, Vd by mu, or rho Vd by mu, which you must have studied in your fluid mechanics. The Reynolds number Rg would be equal to rho Vd by mu. Rho, the mass density, and mu in the denominator is the viscosity. So mu by rho is the kinematic viscosity mu. Kinematic viscosity mu. So Vd by nu becomes V into D is 4R by nu. So 4RV by nu. And that's the Weisbach equation, FLV square by 2GD. HF will be equal to loss of height due to friction is equal to FLV square by 2GD. Please note that some other textbooks may be using 4FLV square by 2GD also, where there is a slight difference for the friction factor and friction coefficient. In our case, F is the friction factor, and the standard notation as specified by the BIS is HF is equal to FLV square by 2GD, but not 4FLV square by 2GD. So in this case, HF, the loss of height due to friction, is equal to FLV square by 2GD. D is 4R, just now we have seen. D is 4R. So substituting that and on rearranging the terms here, FLV square will be equal to HF into 2G4R. HF into 2G into 4R is equal to 4FLV square. Or 2 into 4, 8 G or HF. This is all FLV square. So V square will be equal to 8G by F or into HF by L. V will be equal to taking the square root on both the sides. Square root of 8G by F, square root of R into square root of HF by L. Square root of HF by L. What is the square root of HF by L? HF is the loss of height due to friction over a given length of the control volume. So HF by L gives you the slope of the total energy line. HF by L is the slope of the total energy line, which would be equal to SF. But we are taking uniform flow. So all the slopes are equal, just now we have seen. So the slope of the total energy line is equal to the slope of the water surface, which is equal to the slope of the channel bed, which is S. So HF by L in this case would be equal to S, the longitudinal slope. So square root of R into square root of S. Square root of R into square root of S. So V will be equal to square root of 8G by F into square root of RS. Already we have seen the Cheggy's formula V is equal to C into square root of RS. C is the Chezy's coefficient. So if you compare both the equations, the Chezy's coefficient C can be expressed to be equal to square root of AG by F. The Chezy's coefficient C depends on various parameters. So finding the value of C itself is the toughest job. Once you get the value of C, the velocity V can be calculated, entire uniform flow can be easily analyzed. So to get an equation for C, now it has come almost to a measurable parameters. C is equal to square root of 8G by F. F is the friction factor and G the acceleration due to gravity. So this is how the relation between the Chezy's coefficient C and the Chezy's coefficient C and the friction factor F have been established. C is equal to square root of 8G by F. The third formula that we have used for analyzing the uniform flows is the Manning's formula. This is also a resistance formula which is provided by Robert Manning for uniform flow in open channels. We have been discussing about the analysis of uniform flow in open channels only right now. Let it be Chezy's formula, let it be the Darcy-Weisbach friction factor formula, or the Manning's formula. So this Manning's formula is expressed to be equal to V is equal to the mean velocity at any given section. V is equal to 1 by N R to the power 2/3 S to the power half. In the earlier cases, you must have seen square root of RS. Square root of RS. That means R to the power half, S to the power half is there in the Chezy's formula. But here, R to the power 2/3, S to the power half. So the velocity V is equal to 1 by N, R to the power 2/3, S to the power half is the Manning's formula, where N is a roughness coefficient, which is known as Manning's roughness coefficient. Manning's roughness coefficient. And it's function of nature of boundary surface. So many parameters would affect the value of N, because the boundary sometimes may be smooth, the boundary surface sometimes may be rough, the boundary surface sometimes may be varying from time to time, or it may be varying with the flow parameters. So all this will have a bearing on finding the value of N. But most comfortable, if you know the value of N, the velocity can be computed. V is equal to 1 by N, R power 2/3, S power half. S is the longitudinal slope. You'll be able to find and determine so precisely. R hydraulic radius A by P at any given section, wetted area, wetted perimeter. You'll be able to calculate. But the biggest challenge is finding this coefficient. Let it be Chezy's coefficient, let it be the friction factor F, let it be the Manning's roughness coefficient. Whatever may be the formula that you use, appropriately the value of this coefficient must be estimated. Unless the value of this coefficient is appropriately estimated, it becomes difficult for the calculations. In this case also, if you see this equation, this is not a dimensionally homogeneous equation. If you start writing the dimensional formula, yes, the longitudinal slope, it is a gradient. So m power 0, L to the power 0, T to the power 0 is the m to the power 0, L to the power 0, T to the power 0 is the dimensional formula for S. Then what about the dimensional formula for V? For V, length by time, L T to the power minus 1. For R, A by P. A is L square divided by P is a length dimension L. So it becomes L. So it is a linear parameter. R is a linear parameter. So L to the power 2/3, and this side it is L T to the power minus 1. So you would not be getting a dimensionally homogeneous equation. Just like Chezy's coefficient, the Manning's coefficient also will have certain dimensions. Whenever there is some dimension for the coefficient involved in an equation, you need to be very careful while applying this equation for different unit systems, because the value of these coefficients will be different for different unit systems like FP system, MK system, SA system, CJ system, and so on. So N is a roughness coefficient, and N depends on this nature of the boundary surface, and the dimensional formula for N would be L to the power minus 1/3 into T. MLT system, I'm using M for mass, L for length, T for time as the fundamental or primary dimensions. Okay. So we have, out of these equations, we have most widely used formula like Manning's formula and Chezy's formula. Chezy's formula given by V is equal to C root RS, Manning's formula given by V is equal to 1 by n r power 2/3 s to the power half. Both the equations, both Manning's as well as Chase's, are for finding the velocity only. So why do you compare both? Why do you compare both of these Chase's and Manning's? So comparing both Chase's and Manning's formulae, C root Rs must be equal to 1 by n r power 2/3 s power half, which indicates the relation between the Chase's coefficient C and the Manning's coefficient n. So C into square root of Rs is equal to 1 by n r to the power 2/3 s power half. So on the right hand side you have s power half, on the left hand side also you have s power half. Cancel both the sides, and you have this side r to the power half. Here it is r to the power 2 by 3. So r to the power 2 by 3 minus half. So value of C will be equal to 1 by n r to the power 1 by 6. 1 by n r to the power 1 by 6. This is how the relation between the Chase's coefficient and the Manning's coefficient C and n are related. Similarly, in the earlier case also we have seen how Chase's coefficient and the friction factor F are related square root of 8g by f. C is equal to square root of 8g by f. Okay, so C is equal to 1 by n r to the power 1/6, or C is equal to square root of 8g by f, which is equal to 1 by n r to the power 1 by 6. And so you have the established relation between the friction factor and the Manning's coefficient n also. So F is equal to n square by r to the power 1 by 3 into 8g. This is the relation between the Manning's coefficient and the friction factor. So we have been using three formulas as of now. Chase's formula, V is equal to C into square root of Rs. Manning's formula, V is equal to 1 by n r to the power 2/3 s to the power half. And Darcy-Weisbach friction factor formula, V is equal to square root of 8g by f, square root of R. Yes. Okay. And we established the relation for all the three coefficients also, friction factor F, Chase's coefficient C, and Manning's coefficient N also. You know, various other local resistance formula also. Because these are all semi-empirical formulae where you have the Chase's coefficient C, which depends on so many parameters, Manning's coefficient N, once again depends on various parameters. It becomes very difficult to make use of a generalized formula for all conditions, for all channels. It becomes difficult to have a generalized formula. If you look at the other resistance formula, this is the Ganglion cutter formula. This Ganglion cutter formula is mainly to find the value of Chase's coefficient C. Once the Chase's coefficient C is known, we will be able to establish the relation for the velocity V is equal to C into square root of Rs. V is equal to C into square root of Rs. How to get this C? So Ganglion cutter gave an empirical equation for finding the value of C. C is equal to 23 plus 1 by n plus 0.00155 by s whole divided by 1 plus 23 plus 0.00155 by s into n by root r. This is the equation, empirical equation given by Ganglion cutter for estimating the value of C. What are the parameters involved here? C, R, hydraulic radius can be found, no issue. Yes, longitudinal slope, this also can be found. What else is there in this equation? N is there. N is the cutter's coefficient. This Ganglion cutter's coefficient. Once again, this cutter coefficient also depends on several parameters. Once you know the values of this N, you can substitute here, find the value of C. Once you get the value of C, V is equal to C into square root of Rs provides you the velocity. Another resistance formula given in open channels is Bayesian's formula. Ganglion cutter, then Bayesian's formula. This is also an empirical formula. C is equal to 87 by 1 plus m by r, where m is another coefficient depending on the surface roughness. So looking at all these equations like Chase's formula, Darcy-Weisbach friction factor formula, number 3 is Manning's formula, then Ganglion cutter formula for finding the value of C, then Bayesian's formula for finding the value of C. All these are directly or indirectly working out to find the velocity V. So you have two major equations. One is the Chase's formula, C is equal to square root of Rs. Another major equation is V is equal to 1 by n r power 2/3 s power half. Among these two also, the Manning's formula, estimation of n would become a little easier because changes to C has not been specified how to find the value of C. That is how the Darcy-Weisbach or maybe the Basins or Ganglion cutter try to work out how to find the value of C. But here, this resistance formula V is equal to 1 by n R power 2/3 S power half. R and S anyway can be measured. But to estimate the value of n, there are several parameters which are directly interdependent to find the value of n. So the value of n is highly variable, depends on number of factors, and let us try to see some of the factors how a value of n can be estimated. They are all interdependent parameters. They are all interdependent parameters. What do you mean by this interdependency? There may be one parameter which affects the value of n. There may be another parameter which may be affecting the value of n. These parameter 1 and parameter 2 also are interlinked. Okay, so that is what is interdependent. Number 1, surface roughness. Surface roughness is represented by the size and shape of the grains of the material forming the channel surface. If you take an open channel, the better the channel, the size of the channel may be composing of several soil grains, sand particles, soil particles. So these size and shape of these grains which are forming this channel surface is the surface roughness. Fine grains result in low value of surface roughness n, low value of n. Because when you have a fine grain, they are closely packed and it resembles like a very smooth surface, resistance will be less and the value of n will be less. Coarse grains result in higher value of n. For fine grains, low value of n relatively not affected by the change in the flow conditions, change in the flow stages. But for bigger boulders and gravel, the value of n is generally high, with larger boulders making the channel more and more rough. If the channel surface is smooth, lower value of n. If the channel surface is rough, higher value of n may be taken. So that is how the channel roughness affects the value of n. Once n is known, 1 by n R power 2/3 S power half gives you velocity. But for finding the value of n, we are now trying to ascertain what are the parameters which are influencing the value of n. Roughness, channel bed, channel sides is very, very important. If the channel bed and sides are formed with fine-grained soil particles, the surface becomes smooth, the value of n becomes low. If they are formed with bigger boulders and gravel, naturally the surface is more rough and the value of n also becomes more. Second condition, parameter which affects the Manning's n is vegetation. So whenever a canal is there, you must have seen a huge amount of water may be flowing, but it is not all through the year. There may be some period where the water may be very low, the water may not be available outside the canal. You must observe that. So particularly during the non-monsoon period or summer months, there will be no water in the canal. Since there is no water in the canal, what will happen? Vegetation starts growing there. So after the season is over, once again, if the water is allowed to flow in the canal, this vegetation would be there. So this vegetation also is considered and regarded as a kind of surface roughness because it affects the flow, smooth flow in the canal. It reduces the capacity of the channel and reduces the flow of water in the canal also. So this effect depends on the height, density, distribution, and the type of vegetation also. So what type of vegetation that is growing in the canal bed or what type of vegetation that is growing in the canal sides is very important. Sometimes more height is there, like small plants are grown, naturally they'll give more resistance. And how densely they are distributed along the surface and how the distribution and what type of vegetation is there. Sometimes a small grass may be there which may bend when the flow comes. Sometimes a bigger size, medium size plants will be there. So this type of plants, they resist the flow. So the value of n varies with the shape, cross section of the channel, the slope of the channel bed, also the depth of the flow. So all these parameters with reference to the vegetation affects the value of n. All other factors being equal, lesser the depth of flow, higher the value of n. For example, triangular channel, if you take triangle shaped channel, depth of flow is more. Depth of flow is more. So the value of n is high compared to that of a trapezoidal channel. Also, wide channels has low value of n than the narrow channel. A steep slope causes greater velocity, greater flattening of vegetation, and hence the value of n will be low. This is what is called interdependency of the parameters, as have been mentioned. Third parameter is channel irregularity. This also will affect the value of n. So this comprises of irregularities in wetted perimeter and variations in the cross-section, size, shape along the length of the canal. So when the canal is laid, if there is any change in the size and shape of the channel from one point to the other point, it is called irregular. So this type of irregularity, which will have the impact on the wetted perimeter, also changes the value of n. These irregularities introduce roughness in addition to that caused by the surface roughness. Surface roughness is anyway big boulders, there will be rough. So fine grained soils, smooth. That is the channel roughness. Apart from this channel roughness also, if there is any irregularity with respect to the shape and with respect to the size of the channel, then this will cause additional roughness into the value of n. So gradual and uniform change in the cross section does not affect the value of n. However, the value of n is severely affected by the irregularities that are there in the wetted perimeter, irregularities that are there in the cross section, size, shape of the canal. So abrupt change causes increase in the value of n. Fourth parameter affecting the value of n is alignment of the canal. So when you have a canal aligned, the alignment sometimes may be a smooth curvature may be there with a large radius of curvature. Then the value of n will be very low. But if the curvature is very sharp, because you need to change the direction of the canal, it is called alignment, change of alignment. So if you have sharp curvature with severe meandering, it increases the value of n. So increase of roughness in unlined channels carrying water at low velocity sometimes will be negligible. Number 5, silting and scouring, which I have been discussing about this part of silting and scouring in the earlier classes also. When the flow is taking place, maybe in a channel, let it be a stream, river, or a canal, wherever it is, when the flow is taking place, the soil particles from the side and bed of the channel will have a tendency to get lifted up and flow along with the water. If the velocity is more soil particles will be lifted. Then it is called erosion, scouring. And where does the soil particle will go? The soil particles will carry along with the flow of water, and they settle down at a section where the velocity is less. So under lesser velocity condition, the soil particles will have a tendency to settle down onto the bed and sides of the canal. This is what is called silting or deposition or sedimentation. Okay, so silting and scouring. So both these parameters also will affect the value of n. Silting may change a very irregular channel into a comparatively uniform one, decrease the value of n. Whereas scouring may do the reverse, the value of n may be increased. The sixth parameter affecting the value of managed n is abstraction. The presence of logs, bridge piers, etc. tend to increase the value of n. Whenever a canal is laid, you must have seen a road bridge also will become constructed across a canal because the road is crossing a canal. So how do you take up this? Construct a bridge. The moment a bridge is constructed, so there will be piers, there will be abutments for the bridge. So these piers will be exactly obstructing the flow of water in the canal. It may be sometimes at the middle of a smaller canal. Number of piers may be more in number also sometimes. So this obstruction will have a tendency to increase the value of the managed coefficient. The amount of increase depends on the nature of obstruction, the size of obstruction, shape, and how many number of obstructions are there, how they have been distributed, etc. Next, size and shape of the channel. It is not directly dependent, but any change in the value of hydraulic radius definitely will change the value of managed coefficient n depending on the condition of the channel. If a bigger size, a smaller size. Good shape, irregular, irregular. Naturally, will have the impact on the value of n. Next parameter affecting the value of n is stage and discharge. The value of n in most of the streams decreases with the increase in the stage and discharge. What do you mean by this? Stage and discharge? In a river, during the flood period, huge quantity of water may be flowing in the river. Higher discharge, what we call high discharge. So when more flow is taking place in the river, the water level, the water surface level also rises. This is what is stage. Stage is the level, the depth at a particular section, whereas the discharge is the quantity of water flowing per unit time. So when the water is shallow, the irregularities of the channel bottom are exposed, the effects become significant, the value of n becomes higher. Seasonal change. Owing to the seasonal growth of aquatic plants, grass, weed, and trees in the channel or on the banks, the value of n may increase in the growing season and diminish in the dormant season. So seasonal growth, as I have been indicating, all through the year there may be no water in the canal. There may be no water in the canal. Or similarly, all through the year there may not be the same amount of stage and discharge in the river. It may be varying. During the monsoon period, huge discharge may be flowing in the rivers. During the non-monsoon period, very low discharge may be flowing. So at the sides and at the bottom of the channels, there may be plant growth. So this plant growth, grass, weed, sometimes trees may be there in the channel banks. They may affect the value of n, and the value of n may be increased when they are in the growing season. When these things are growing, because they abstract. When more abstraction is there, more value of n. During the flood period, when the water is continuously flowing, these plants, trees, weed may not be having much of effect because they may die also. So in the dormant season, this may diminish. This may diminish. The 10th parameter is suspended material and bed load. The suspended material and bed load, whether moving or not moving, would consume energy and cause loss of head or increase in the channel roughness. So suspended material means small particles, soil particles, because of the velocity of flow of water, may get lifted and flow along with it. Either suspended load. Where there is a lesser velocity, they may settle down, it becomes a bed. It becomes a bed load. So all the above factors should be studied and evaluated with respect to the conditions regarding type of channel, state of flow, degree of maintenance. All these things are required to be taken in conjunction. Together they must be studied. They provide a basis for determining the value of the Manning's roughness coefficient n for a given problem. You see, the formula appears to be so simple. V is equal to 1 by n, r power 2/3, s power half. Changes, I mean the Manning's formula. Similarly, the changes formula V is equal to c into square root of rs. But getting the value of these coefficients is very, very important. So many parameters will influence the value of n, as we have seen now. So in general, conditions tending to induce the turbulence will increase the value of n. Those tending to reduce the turbulence will decrease the value of the resistance. That is why it is called Manning's resistance coefficient. Resistance coefficient. So recognizing several primary factors affecting the roughness coefficient, Cohen developed a procedure to estimate the value of this n. So how to get the Manning's n? Manning's n would be equal to n0 plus n1 plus n2 plus n3 plus n4 into n5. This is what he tried to develop an equation for estimating the Manning's n. n0 plus n1 plus n2 plus n3 plus n4 into n5. So what is this n0? n0 is a basic value for a straight, uniform, smooth channel. That means which is not affected by any of the above parameters. That is n0. The value of n0 may be usually of the range of 0.02 to 0.028. I repeat once again. Straight channel, uniform, smooth surface. What is the problem? There would be no problem. So the value of n0 in that case would be taken to be equal to 0.02 to 0.028. Then this n0 used to be added with several other values of n1, n2, n3, n4. What is n1? n1 is to be added to correct for the effect of surface irregularity. If the surface is irregular, you have a maximum value to be equal to 0.02. If there is no effect of this irregularity and with every regular shape 0. So N1 may be varying from 0 to 0.02. N2, a value for variations in the shape and size of the channel cross section, 0 to 0.015. N3, for the obstructions, 0 to 0.06. N3, 0 to 0.06. N4, a value for vegetation for a given flow condition, 0.005 to 0.1. N5, a correction factor. This is a multiplication factor. You must have seen in the equation N0 plus N1 plus N2 plus N3 plus N4 into N5. So this N5 is a correction for the meandering of the channel, may be varying from about 1.0 to 1.3. What do you mean by the meandering? It is the change in alignment of the channel sections. Quick change in the alignment of the channel section. If you take a river, how the river may be taking very irregular shape from one point to the other point, changing its direction. This is what is called the meandering, river meandering, actual shape through which the water may be flowing, river shape. Okay, so sometimes there may be straight path also. So in a channel, if you take in a canal particularly, there may be no change in alignment, straight for about 100 kilometers, 150 kilometers, it may be straight. Then it may take a long curvature and then take its change in direction. So N5 is a correction factor for meandering of the channel, may be varying from 1.0 to 1.3. Taking all these parameters, you will be able to arrive at N0 plus N1 plus N2 plus N3 plus N4 into N5 you see the value of N. Okay, so today's class, we have seen about the uniform flow. What are the main features of the uniform flow? Starting from the simple definition of a uniform flow where the depth of flow remains constant along the channel direction. So Y1 would be equal to Y2. Since Y1 is equal to Y2 for a prismatic channel, A1 will be equal to A2. And the discharge equation and the continuity equation Q is equal to A1 V1 is equal to A2 V2. Hence, the velocity V1 also would be equal to V2. So, another feature is V square by 2G becomes constant. Since V1 is same as V2, so V1 square by 2G will be equal to V2 square by 2G. Since the intercept V1 square by 2G equal to V2 square by 2G, you have equal slopes for the channel bed, water surface, total energy line. So, three main features of the uniform flow are being discussed. Number one, Y1 is equal to Y2, the depth of flow remain constant. The velocity also will remain constant from one section to the other section along the length of the channel for uniform flow. Number three, the slope of the total energy line is equal to the slope of the water surface is equal to the slope of the channel bed. SF is equal to SW is equal to S0 is equal to S. So these are the three main features of the uniform flow. To analyze for this uniform flow, you have several equations which are semi-empirical in nature. Chayes' formula, we have reduced CV, the velocity V is equal to C into square root of RS. Manning's formula, V is equal to 1 by N R power 2/3 S power half. Another empirical formula. Then about the Darcy-Weisbach friction factor equation, V is equal to square root of 8G by F into square root of RS. Then the basis formula, then the Ganglion cutter formula to work out for the Chayes' coefficient C. Once the value of C is known, we will be able to arrive at the velocity, and hence the uniform flow along the canal can be analyzed comfortably. Similarly, if you want to make use of the Manning's formula, the value of the Manning's coefficient N must be known. V is equal to 1 by N, R power 2/3, S power half. S, longitudinal slope, can be measured exactly, or hydraulic radius can be known A by P. What is missing there is the value of N. So to estimate the value of N, several parameters are given here, and what factors the value of N gets influenced, based on which Cohen has developed one equation to estimate the value of N as N0 plus N1 plus N2 plus N3 plus N4 into N5. N5 is of course for the river meandering the channel, meandering 1.0 to 1.35. Straight reach, there is no change in the alignment, no change in the meandering. So value of N5 would be equal to 1.0. If it is having huge changes, then it will be maximum of 1.3. So by choosing the appropriate values of these N0 to N5, you will be able to estimate the appropriate value of N, which can be used for finding the velocity V in Manning's formula. So this is how the uniform flow. In the coming class, we try to work out some of the problems for analyzing the uniform flow by making use of these formulae. Thank you very much. Thank you. I stop here at this stage. And if you have any questions, I'll be able to clarify you. And if there are no questions, thank you. And we meet in tomorrow's class. Thank you very much.